Hello. Okay, so I'm back with the second part of this video, still talking about this idea of redundant vectors and linear independence and dependence, and we are just starting to talk about basis, so I'm gonna jump back into that. So if you remember, we just did an example, and we kind of came up with the idea that after we'd done the whole example problem and everything, the non-redundant vectors were v1 is 1, 1, 1, and then of course v2 is 1, 2, 3. And the book wants us to know that these are then the basis of V, right? So they form the basis of V equals the image of A, right? So they're both the basis and the image of A. But we already knew they were the image of A. Let's talk about what basis means. The basis of the image. Okay, so the definition that we're given is that, we already talked about this, they form the basis if they span V and are linearly independent. But as for how to find the basis, list all of the column vectors of A and omit the redundant vectors. And we can see this is what we did here. These are the non-redundant vectors left over from the column vectors. But I think one thing that the book really makes a big point about pointing out is how we actually find out the redundant column vectors. So first they give us a handy little trick that will work sometimes, but not always. And they ask us if the following vectors in R7 are linearly independent. So we start out with our first vector being 7, 0, 4, 0, 1, 9, 0. Then we move on to our second one. That's 6, 0, 7, 1, 4, 8, 0. Move on to our third one. We've got 5, 0, 6, 2, 3, 1, 7. And then we move on to our very last one, which is 4, 5, 3, 3, 2, 2, 4. Okay, so we want to know if these are all linearly independent, and if not, which ones are the redundant vectors. Okay. So the book circles this 1, this 7, and this 5. Why does it do that? Well, it does that because along this row, everything before has been a 0. Along this row, everything before has been a 0, and along this row, everything before has been a 0. And if we think about that, if we're going to try to say that this vector is a linear combination of these two vectors, well, what possible linear combination could happen where you multiply something by 0 and add it to 0, and it equals up to a new number? Well, it can't, because anything times 0 is 0, and 0 plus 0 is 0, right? So obviously this one cannot be, a redundant vector. And that's the same for all of these, right? This one can't be because it can't be a combination of these last two, and this one can't be, right? And obviously this one's not because it's the first one on the list. So that's how you prove that none of these are redundant, which leads us into a theorem called linear independence and zero components. So basically, so we're considering vectors v1 through vm and rn. I'm not going to write that out. But if we have v1 is non-zero, and if each of the vectors vi, where I is greater than or equal to 2, right? Because it has to be bigger than 1, has a non-zero entry in a component Okay, in a component where all the preceding vectors have a 0, then the vectors are linearly independent. Just another way of writing out what we just said. If you've got a non-zero component where all the other ones before that have been 0, then it's going to be linearly independent. Okay. So we then have another example, which is what do we do if we have, if 0 is not involved, right? Like, how do we know if that's not something we can rely on as a test? So they give us the vectors 1, 2, 3, 4, 5, 6. Let me zoom out a little bit. And 7, 8, 9. Okay, so there are no 0 components, right? We can see that V1 and V2 are obviously non-redundant because V1 is non-zero and V2 is not any kind of scalar multiple of V1. But to figure out whether V3 is redundant, we really need to figure out if we can say that V3 equals C1 V1 plus C2 V2, right? This will tell us if the very last vector is redundant. So the way we set this up is with an augmented matrix. So we do 1, 2, 3, 4, 5, 6, equaling 7, 8, 9. And of course, we get a reduced row echelon form of 1, we've got -1, 2, and 0 on the right side. So in other words, what that means is that, in fact, the last vector actually is a linear combination of the other two. And our C's are going to be -1 and 2, like it says right here. So in other words, V3 is going to be equal to -V1 plus 2V2, right? We can see that right here because we've got the reduced row echelon form for V1 corresponding to -1 and V2 corresponding to 2. So it turns out that vector 3 is obviously redundant. Now let's think about how we would write this. A lot of the times, mathematicians, they like to do this. They like to set things equal to 0, right? So right now we've got this in the form V3 equals -V1 plus 2V2. But we could also write this as V1 minus 2V2 plus V3 equals 0, right? Just a simple, basic algebra, right? And as a reminder, I'm not writing arrows over these V's, but they are vectors. So this equation is called a linear relation. When you take kind of this kind of thing right here and you set it equal to 0, you move things around and you set it equal to 0. That is an example of a linear relation. So now I'm going to give a bit of a theorem about linear relations. Now, don't forget that I just showed you a method of figuring out if vectors are redundant if there are no 0 components. Don't forget that because that will be helpful. But we will move on to linear relations. Okay. So that, what I just spoke of right there, a C1 V1 plus all the way up to C M VM equals 0 is a linear relation. Now, there is always something called a trivial relation. That's a relation where C1 all the way up through Cm is equal to 0, right? And every single, relationship, every single vector, every single set of vectors, that's going to be true, right? Every single time you've got a scalar of 0, no matter what the situation is, that's going to equal 0. Now, non-trivial relations, where at least one of the coefficients is non-zero, may or may not exist. And think about that, because what we were doing is we ended up with this linear relation because we went through a whole process to show if these two vectors were linearly independent or not. So yes, you guessed it. There's another theorem right after called relations and linear dependence. It basically says that vectors are only linearly dependent if there is a non-trivial relation among them. We can tie this back to our example. We found a non-trivial relation, and yeah, it's linearly dependent. Okay, so if we say that they are linearly dependent, let's see, just reading through. Okay, so if we've got something being linearly dependent, the book is just kind of saying what we already did. You can take something that is in the form of this and turn it into this, and that becomes a non-trivial relation. There's also a converse way of writing this. So conversely to that fact, if we've got a non-trivial relation, then we can end up solving for VI and then expressing VI as a linear combination of the preceding vectors. In other words, we can go backwards, right? So we can take something like this, and we can go back to this. So you can move from either way. You can move from here to here or from here to here, right? Which is pretty straightforward, just like, use your common sense there. But let's see. Let's think about, this next thing is about the kernel and the relation. But okay, so this kind of just continues on from what we were saying. So basically it says that we've got column vectors of an n times n matrix A that are linearly independent, and they want us to find the kernel of matrix A, right? So in this case, A times vector X equals the 0 vector is also the same thing as saying V1 Vm times X1, we get the gist, through Xm equals 0. Now we can dot product this, right? This looks familiar. So it becomes X1 V1 plus Xm Vm equals 0. So in other words, we see that finding the kernel amounts to finding the relations among the column vectors of A. Right? because, you know, if we look at this, we've got this set equal to 0, right? And it's in the dot product form. And to figure out what the kernel is, we really need to figure out all of the scalars, all of the x's, basically, that will work for this relation, right? And right, so we need to figure out all the x's that will work for this relationship and make that true. I can check with Dr. Prudham, but I'm pretty sure we're not looking for the v's here. We're not looking for the vectors. Oh wait, no, yes we are. I apologize, deeply apologize. We're looking for so we're looking for the relations among the column vectors. Actually, that's something I'm going to check with Dr. Prudham on. I am not fully, from later examples that we see in the book, they kind of say that we're looking for the x's, right, in this scenario, and those x's, we can pull those out, and that becomes our kernel. But one would imagine it would be the vectors, right? Because when we talked about kernel in the past, it's the span of vectors. But I think maybe they mean you make a vector with the scalars. I know that I'm not really making any sense right now. From what I can best surmise before talking to Dr. Prudham about this, the point is that you look at a relationship like this and you find all of the possible scalars. Yes, you find all the possible x's such that those x's times the column vectors that you're given equals 0. I'll write this down. It might change in case I'm wildly off, but I think I'm right. So you find all of the x's such that the x's times the column vectors equal 0. And you take those x's and turn them into vectors. Like, for example, if you've got 1 times v1 plus negative 2 times v2 plus 3 times v3 equals 0. You do 1, negative 2, 3, and that becomes a vector, and that is part of the kernel. So that is what I've seen from other examples. It's just kind of like another way of thinking about it from the dot product. But I'm going to stop us here, and I'm going to come back next week and finish off this lesson. There's really not much more to talk about. Really the only thing that we end up talking about is, I think we give an example of what I just explained about this other way to find kernel. We kind of go back over the characteristics of linear independence and how that works. And then we have a little bit more about basis. But to do a really quick recap of what we did today, we went over the definition. And in fact, I'll write this out. We went over the definition of a subspace. We figured out that kernel and image equal subspaces. Right. Then we looked at defining what is in a subspace based on the number of dimensions. This is where we kind of got into that whole, you know, if you're in R3, then you've got R3 as a subspace, and the plane's going through 0, all that kind of stuff. Then we went through redundant vectors and how to find redundant vectors using both the zeros, if they're available, like zeros in the components, if they're available to us, and if not, we use Gaussian elimination. From redundant vectors, we moved on to linear independence and dependence, and moved into basis, which of course is based on that because basis relies on both span and being linearly independent. From then we looked at linear relations, which is really another way of writing the linear combinations that make up a redundant vector. Right, we connected types of relations to independence and dependence. And that is kind of, oh, and the last thing that we did is we thought about using the dot product to find your kernel. So we got through a good bit today. So I hope you enjoyed, and I'll be back next week to finish off 3.2.